So now we need to talk about power internal resistance. Remember back from mechanics that power was defined as work divided by time. How fast do you do work? So to come up with an expression for this for electricity, work, remember, is equal to the opposite of change in potential energy. So I don't want to deal with negative signs, so I'm just going to do absolute value. And then change in potential energy is equal to charge times potential difference. So what potential difference did this charge move? That's how much work was done by the electric field in moving it. So if we go back to our power definition, our work, which ends up being Q delta V over T, well, notice we can isolate Q over T times delta V. This is current. So we get I times delta V. Now, I usually drop the deltas in this unit, so I'm going to write P equals IV. And that's the way that most of us remember power, current times voltage. So you can substitute in, using Ohm's law, V equals IR. So if you substitute in for V, this is also I squared times R. If you rearrange for I, which is V over R, then you get V over R times V, so V squared over R. So please notice again, if we go back to capacitors, the energy stored in a capacitor is 1/2 QV equals 1/2 CV squared equals Q squared over 2C. So the 1/2, which came from the calculus, but I and Q, and oh, I wrote this wrong, 1/2 QV, bad teacher, because that should match up. And then this one goes over here, we've got V squared, but instead of times C, we divide by R because of that reciprocal thing we talked about with the way resistance is defined versus capacitance. And then I squared times R, well, Q squared divided by C, and then the 1/2. So that's the first half of the video. The second half might take a little bit longer. We're going to talk about batteries. Batteries are an energy source from chemical reactions. So as the chemical reactions proceed, there's less and less reactant, there's more and more product. And for the first long life of the battery, you don't really see a noticeable difference as you're using up more of the reactants. But as you're using more of the reactants, converting them into products, it's sometimes then hard for them to get the electrons to get through the rest of the material to get to the two ends, or to come out the negative end. So we define a battery as two different ideas electrically. We have a source of EMF, and I will explain that in a moment, and an internal resistance. And you really can think of this as those electrons, as they're continuing in the reaction, having a hard time finding their way through the goo inside. So as a battery ages, we'll say this internal resistance increases. That's a direct result of the chemical reactions. But this is a much easier way to keep track than like how much of each reactant do we still have, and it works very well. So EMF. EMF is a very old term, and it refers to electromotive force. So break down this word, electro, so electronics, motive, move. So EMF is the force that makes electricity move, except it's not a force, it's a voltage. This is potential. So except for explaining what EMF stands for, we never use the term because it's not a force. It doesn't produce acceleration for a particular mass. The reason that charges move in a circuit is because of the potential difference of the two ends of the battery, or the voltage of the battery. Now the symbol we're going to use for EMF usually is going to be the epsilon, so a curly E. But again, remember, now we're using a different symbol for EMF for the inside of the battery, the energy source, but it really is just a voltage. So the way we're going to draw this in a circuit is if this is just the battery, and we're going to start A and B in the circuit. So this is the source of EMF, the symbol we've been using for the battery, so potential. And then this is the internal resistance. And the way these are often drawn is a little box around them. to say that these are not two separate devices that you connect in the circuit. These are the two ways we keep track of what's going on inside a battery. So if you just have a battery not connected to anything else, if you measure with a voltmeter the potential difference between A and B, because there's no current flowing, because we don't have a complete circuit, the potential you're going to measure is equal to the EMF. So this is called the terminal voltage, because you're measuring between the terminals of the battery, like the 2 prongs on the 6 volts or the 2 ends of a AA. And this is called the open circuit voltage. So a mistake I made a long time ago when I was testing batteries before using them with the lab is I took a voltmeter and I measured across a bunch of bare batteries, and I always got that they were 1.5 volt D-cell batteries. They were all 1.5 volt. And then we put them in the circuit and the light bulbs barely lit up, because this is with no current flowing, there's no loss of voltage across the internal resistor. But now, if we put it in the circuit, so I'm going to recopy. So here's A, the source of EMF, the internal resistance, little r, put a box around it. Here's point B, the exit point from the battery. And now I'm going to attach a load resistance to it. So now there's going to be current. To get that amount of current, we're going to apply V over R, the general one, total. I'll say it that way, not this big R. So the potential source in the circuit is the EMF, but then the resistance, we have 2. And so the question is, are these in series or parallel? I know we haven't done that yet in this unit, but we did in the last one. See, there are no choices here. This is one big loop. These 2 are in series. So the total resistance is the sum of the 2 of them. So the current is not the energy source divided by the load resistance. It's the energy source divided by the sum of the load resistance and the internal resistance. So you can see as the battery ages and the internal resistance gets bigger, this current is going to decrease. So over time, eventually, this, if this is a light bulb, is going to be less and less bright. So now let's talk about this terminal voltage. We can measure it 2 ways. This terminal voltage, we have a source of energy, and then we have some being used up. The potential across this, V equals I times R. So the potential across the whole battery is EMF minus the current times the internal resistance. Or, if I slide along the wires here, it's the same potential difference across big R. Well, potential difference across the resistor is I times R. So this, again, remember, VAB is called the terminal voltage. And it's not equal to EMF anymore because this is under load, is the correct terminology to use. So when you actually have a battery in a circuit, unless its internal resistance is extremely small, you are going to get less current out of it than you expect. So let me just write that down. The terminal voltage is always less than the EMF under load. And so you're going to do some problems with that, but that's how batteries work. And we will move on to series and parallel next time.